Dr. Bala Krishna Prabhu S from College of Engineering Guindy, Anna University, Chennai. And since morning and since yesterday rather, primarily we are focusing on fiber reinforced composite. We'll have another aspect of the composite industry, that is challenges in metal matrix composites processing and mass production. So over to you, Dr. Bala.
Yeah, thank you very much, the organizing team, and especially Dr. R.K. Singh sir for giving me
Sir,
an
may I
opportunity.
request you to please place the mic suitably? Your voice is quite less.
Okay. 1 minute.
Just 1 minute, sir. Sir, can you just unshare the screen? Sir, you can start now, sir. Sir, am I audible? Sir, your voice is not coming, sir. I think you are on mute. No, sir, you are not audible. Just a minute, sir. We can't hear you.
हेलो सर को बोलने को बोलो
Sir, probably your microphone is not connected. Can you please unplug once? If you can hear me. Hello? Hello? No, sir, we can't hear you yet. Could you please unplug? Can you hear me? Just raise your finger or thumb so that we get to know. Okay, fine. So,
I can hear. Can you hear my voice?
yeah, loud and clear now, sir.
Now loud and clear. Okay, okay. I think I can go without a microphone. I think the microphone has created some problem. I think now you are audible. My voice is audible.
Yeah, please go ahead, sir.
Yeah. So thank you very much for inviting me to deliver this talk on the challenges in metal matrix composite processing and especially in mass production. And you might have come across the polymer matrix composites, and also you have witnessed several components and applications make use of this polymer matrix composites. And in our day-to-day life, we might have come across so many components that are, as a result, see, the polymer matrix composite processing is very well established, and as a result, it has penetrated into the industry market. Now, the metal matrix composites, even though no, you have very good mechanical properties and very good benefits, and this metal matrix composite still it has a lot of problem. As a result, it is not penetrated into a industrial market. So the problems that are hindering this the market penetration, probably in the research aspects, we will address. So as you know, the metal matrix composites in general consist of two or more chemically distinct macro constituents separated by a distinct interface. Sometimes in the metal matrix composite, we used to say interface because the interface is a common terminology. And in this composites, we the high temperature processing involved in it, we end up with the interface. A different pace will be generated at the interface. So as a result, it would be interface. So usually these kind of MMCs can be made from pure metal or alloy. Sometimes, most of the cases, we go for alloy metal, and especially with the non-ferrous metal. So aluminum alloy or magnesium alloy or copper alloy, we try to convert that into a composites. As a result, the weakness of the metallic material will be overcome by reinforcing the reinforcement. And also we have a higher ductility and toughness than the ceramic and CMC. And also here the role of the reinforcement in MMC is to increase the strength and modulus, as similar to the polymer matrix composites, where we improve the strength and also the toughness and modulus. Similarly, in the MMCs also, our main objective is to increase the strength of the metal and increase the strength modulus of the metal, so by reinforcing. So, and also the MMCs have temperature capability generally higher than the polymer. So the thermal stability of these metal matrix composites are little higher than the metal. As a result, you have a very good high temperature capability. Then low to moderately reinforced MMC is formable via processes normally associated with the unreinforced metal, meaning what all the conventional methodology you have to process the metal, the similar methodology we can also adopt to manufacture or process metal matrix composites. As a result, the technologies are not new. It is only the modifications of the conventional technology that we employ to manufacture metal. So therefore, the technology wise, it is not a newer technology that we are going to talk about. It is all conventional technology, but we need to have some kind of a little modification to manufacture or process composites. These are all some basic things that the metal matrix composites can be classified into dispersion strengthened, particulate strengthened, and fiber reinforced. And especially the fiber reinforced would be similar to the polymer matrix composite, where we have a lot of opportunity with respect to the particle reinforced composites and dispersion strengthened composites. These are all distinguished only with respect to the particle dimension. If the particle dimension is more than 1 micron, we used to call that is a particle reinforced. And if the particle dimension is less than 1 micron, we call that is a dispersion strengthened MMC. So the principle is very simple. In the fiber reinforced composites, the fibers take up the strength. So that is a major load carrying member. And as a result, the strengthening mechanism is fiber strengthening mechanism. But in particle reinforced composite and dispersion strengthened composite, the particles that will be acting as a hindering element to dislocation movement. As a result, now you have good degree of improvement. So in general, now we have aluminum, magnesium, titanium, copper alloys, super alloys, and majority of this metal matrix composites were already tried with aluminum and magnesium. And we take this reinforcement, mostly the silicon carbide, graphite, or alumina, so in the form of a particle or fiber or in the form of a whisker. So coming to the processing technology, and if you want to have a mass production, and we are depending on two technology. One is solid state processing and liquid state processing. And in the vapor state processing, somehow you can make a batch production. And for high-end application, we still fabricate some of the MMCs with the vapor state processing. And solid state processing technique also possible with mass production concept, but because of the size limitation and also some of the inherent problem associated with the composite technology when you take up the solid state. And so far it has not been fully used for commercializing the metal matrix composite, but the research field we are using the solid state processing to demonstrate some of the mechanical properties of metal matrix composites. So the liquid state processing from the industrial perspective, it would be the convenient method to have a mass production technology of metal matrix composites. So here we have three different stages of pre-processing and primary processing and also secondary processing. And this liquid state processing technology especially useful for particle or short fiber or a chopped fiber, or probably for a continuous fiber also in case of a preform preparation. And the major technology associated with the liquid state processing are stir casting, then we have an infiltration, then we have a spray casting technology. And among this, the stir casting is the one of the important technology where there is a possibility of mass production. So it is a conventional technology, little modified. So in the primary processing stage, why it is called a stir casting? Because we add particles or chopped fiber or short fiber and try to stir it to homogenize this particle distribution or short fiber distribution. So stirring is necessary to have a homogeneous distribution. So once the stirring helps to have a homogeneous distribution of these reinforcements inside the metal, then the conventional casting methodology will help, where you cast it and then try to have a secondary machining operations or joining or whatever purpose for which you are making this composites. And in the infiltration process, the preform will be prepared either out of a continuous fiber or a short fiber. And by the infiltration, like a gravitational infiltration or pressure assisted infiltration, you try to infiltrate the liquid metal, and finally you end up with the composite. So the spray casting, where you are going to spray the liquid metal over the reinforcement and layer by layer, and then try to consolidate. Now what I am going to talk about, it's only the liquid state processing, because that is only the technology. Probably if you overcome the barrier of these technologies, then there is a possibility of mass production. So the industry can think about making some good composites in a mass production and then use it for a different application. So in the stir casting and the liquid state processing, where the stir casting, we can have a metal yield of 90%, and then range of volume fraction of reinforcement addition is 0.3. That means 30% of reinforcement in terms of a volume that can be reinforced. And also no damage would occur for this reinforcement, and it is least expensive. And associated technologies of this liquid state processing, we have a skew casting. Then in the skew casting, we can go up to 45% volume fraction. That means in the fraction it is 0.5, in terms of percentage 45. But sometimes you have some damages on the fiber or particle because the pressure is applied, and also it is moderately expensive. And the powder metallurgy compared to the liquid metallurgy, it is highly expensive. So for a commercial production and for a mass production, it would be possible to take a stir casting technology. The technology is very simple. No, you try to heat the metal and make it in a form of a liquid and superheat the liquid and try to add the particles, whatever may be the reinforcement particle, silicon carbide or alumina or any other particle you're going to add and try to stir it mechanically or probably ultrasonically. So some kind of a stirring to create turbulence is necessary so that the particle will homogeneously mixed and it will uniformly distribute. Once it is distributed, then by conventional way of deposition, that means casting certification, you can do it. So these are some of the microstructure in our laboratory that we have casted. So you could be able to see the particle distribution, which are in some cases it is agglomerated. The particles are agglomerated. Some places the aluminum is left without any particle presence. That means the microstructure is highly inhomogeneous. It is not homogeneous microstructure in some of the cases. In some of the cases, we could able to achieve the microstructure uniformity. That means, the particles are well dispersed and there is no agglomerations possible here. And when you have so much of agglomerations, one thing that is noticed here, it's that, so you could see a lot of porosity associated with the agglomerated structure. And that's one thing. So because melt will not be allowed to go inside the agglomerated structure, so melt will be stopped here. It's a barrier. So as a result, now you form some porosities also associated with the part clusters wherever now you have. But when you have a kind of the uniformity, there is a homogeneous distribution, and you can also minimize the porosity, and you can also expect it to have good mechanical properties associated with this processing condition. In general, even though this technology gives a possibility of mass production, but there are some challenges that are associated with this technology. Is that the one thing is difficulty of achieving a uniform distribution of reinforcement material. See, that is the one foremost challenge of this technology. So once you achieve a homogeneous distribution, that you can also work on improving the properties of this material. Another thing is that the wettability issue, because the metallic material and a ceramic material you try to bind, and as a result, the wetting would be the problem. Another case is the chemical reaction, because most of this liquid state metallurgy processes will take a minimum 30 minutes to an hour. As a result, there is a continuous contact of this reinforcement into the melt at high temperature, slowly develop some reactions between the matrix material and reinforcement material. So you generate some chemical reaction product at the interface. Sometimes that gives you an undesirable byproduct that stops the bonding between the matrix and reinforcement. So as a result, we cannot get composites with good mechanical property and good reliability. So the porosity can be eliminated. That is not at all a problem in a mass production. So we have a technique to control the porosity. But the main challenges in the metal matrix composite production is the three, I would say: difficulty of achieving uniform distribution of the reinforcement. Then we have the porosity, the chemical reaction, then the wettability. See, the uniform distribution, supposing, for example, if it is controlled by the viscosity, and here we have a viscosity relationship here, which is the inverse proportion. So the relationship between the viscosity and temperature is given here. It has an inverse proportion. That means when the temperature is high, melted temperature is high, the viscosity will be lower. So when you have a melt which is kept exactly at the melting temperature and addition of reinforcement in it, the reinforcement absorbs the temperature. As a result, the melted temperature will be drastically reduced. As a result, now viscosity will be very, very high. So it won't allow the particle to disperse inside the matrix material. So because it is highly viscous, it will never allow the particle to penetrate into the viscous medium. And as a result, more agglomerations would be formed. So if you conveniently set the temperature parameter a little high, you will have a lower viscosity, which will be sufficient, where the particles will be penetrated while the turbulence is created. It will go around and then uniformly distribute. So one controlling parameter in this process is the temperature. So the temperature may play a major role in controlling your particle distribution. Okay, so by controlling, probably here you have a data which we have calculated that the aluminum alloy, the viscosity is drastically reducing from the melt temperature to 900, but when I add 10% of silicon carbide particle, the viscosity is even very high. So that means it is high viscous medium. So distribution is very, very challenging. So probably at 900 degrees centigrade, I would get the viscosity similar to the pure metal. So that would be possible where now you can disperse this what is known as the particle. So here I present the three cases. One, the melting temperature 650 where preheated to 700 degrees centigrade, where particles are stirred and casted. Finally, at 700 degrees centigrade, we end up with a more amount of agglomerated kind of a structure. So silicon carbide particle, I could see agglomerated form. And when I try to increase the temperature to 800 degree, the agglomeration was broken and you can able to see a good homogeneous distribution of this particle. And again, when it is increased to 900 degrees centigrade, further agglomeration starts. So that means, the temperature, only by increasing the temperature, one cannot achieve good homogeneity because something is happening there. So you have to have a sufficient viscosity to allow the reinforcement to penetrate and then uniformly distribute. But even if you have a too much of low viscosity, that try to allow the particle to settle down very quickly a moment you stop the process and before the casting. So that also try to make more particle agglomeration. So therefore, extreme lower temperature is also not favorable and high temperature is also not favorable to have a homogeneous distribution of a particle. That results in mechanical properties also. See, when you have a 800, you have a homogeneous distribution. As a result, now you got to have a good mechanical strength compared to the parent 700 degree processed condition. Okay, but in the 700 as well as 900 degree conditions, the strength is also declining. That means one has to optimize what would be the temperature to get homogeneous distribution. So the temperature effect we have studied. Then also another important thing is the wettability between the main substances. So it's the ability of a liquid to spread on a solid surface. So that means, one can increase the wettability by increasing the surface energy of a solid, that means reinforcement, and decreasing the surface tension of a liquid, that means the matrix metal. So the decreasing surface tension of the matrix metal in the liquid is possible by increasing this temperature. So the viscosity will come down. And again, increasing the surface energy of the solid is by means of heating the solid, preheating the solid. So these combination will make a decreasing solid liquid interfacial energy at the particle matrix interface. So the wettability can be decided with the angle, wetting angle. So you have a tension vector. So it is surface tension vector of solid liquid and surface tension vector of liquid vapor. So the angle between that. So if this angle is 0 or close to 0, we call perfect wetting. And preheating the ceramic particle to 1100 degrees centigrade gives the angle 45 degree compared to 900 where you have an angle 150. So therefore, preheating the particle before adding into the melt helps to improve the wettability. Okay, and also another way, so the agglomeration, it's not only happening because of the settlement of particle, because of the lower viscosity. It's also possible, redistribution is also possible because during the solidification, the metal try to solidify. As a result, you generate some kinetic energy in the solidification front that pushes the particle in the front of the solidification. As a result, you have some agglomeration possible. So if you control that driving force by applying a compressive force over that, then homogeneous distribution, what happened in the melt would be produced in the solid after casting also. Therefore, the skews casting would be the another secondary operation. Once the stirring is over, then you can probably transfer the melt to the process where you do a skews casting, where you can also get some good microstructure that helps to improve the mechanical property. So here, these are all the process parameter that we have studied, from varying the melt temperature from 700 and 750 to 900, and keeping the die temperature also in a different situation, 250 to 400 degrees centigrade. And also by changing the pressure from 30 MPa to 120 MPa, how microstructure is changing, that we have seen. And this zero skew pressure is something like a conventional casting. So that clearly indicates that you have a lot of agglomeration. Even though you assume that, in the melt, you have created good condition where agglomeration is not there and you have a good homogeneous distribution. But after solidification, you could see a lot of agglomeration. This may be because of the solidification nature that push the particle to the front and you get agglomeration. But when you try to increase the squeeze pressure and also keep some 400 degrees centigrade die temperature and 800 degree what is called the melt temperature, you could be able to see that a homogeneous distribution was possible with some 100 degree, 100 MPa pressure and 120 MPa pressure, 130 MPa pressure. I could see homogeneous distribution. That means, see, moment we have a solidification start, this melt, once it starts solidification, then it disengages the melt from the solid, that means die. The mode of heat transfer would be converted from conduction mode to convection mode, and it is a slow process. So during the slow process, they try to create a lot of agglomerations. But moment you have a pressure that is applied, the solid will be engaged with the die walls, and the mode of heat transfer is only the conduction mode of heat transfer, and also we're applying a negative pressure. As a result, the particle movement inside the melt will be stopped, so it would be intact with the melt. And once when you are solidifying, when it is solidifying, it's not trying to move out. So that means if you look at this pressure range 700 to 130, you could get some homogeneous distribution, and as a result, now we can also expect to have some grain size reduction possible, because you are trying to create a situation where the mode of heat transfer is conduction mode, where the grain, because it's a faster solidification, as a result, the matrix itself now has grains dimension which are in a finer domain. But whereas in the case of a conventional casting, it ranges from 10 micron to 40 micron. But in the case of a skew casting, sometimes you can see the ranges from 2 micron to 14 micron. And also there is a greater improvement in the strength is also possible. And ultimate strength from some 70 MPa, it reaches to 250 MPa. So, and also the another important thing is the ductility will reduce. That's another challenge. But the thing is, the mechanical property, especially the tensile strength, keeps on increasing with respect to this processing condition. So therefore, this is another one way where, see, if you couple these skew casting also along with the stiff casting, you can able to get some good mechanical property and also good microstructure. See, the interface, as I said, it's another problem where, because the chemical reaction will induce some kind of a different phase formation at the junctions of boundary of both matrix and reinforcement. So here, the possible reactions in this case, especially when you have different material system, when you most probably we take aluminum as a matrix material and silicon carbide or boron or carbon as the reinforcement. In these cases, especially in aluminum silicon carbide, we get a different product which is called Al4C3. It's a compound. It's a compound that is formed at the junction, which is a nice precipitate around the boundaries of this particle that stops the connection between the matrix and reinforcement. And also sometimes it weakens the bonding at this junction. So because to understand, so for every case, you have some byproduct which stops the bonding between the matrix and reinforcement, and also sometimes it weakens the interfacial bonding because of the nature of the phases that are formed. So we have also extensively studied this Al4C3 formation. Okay, so which is formed by aluminum and silicon carbide. Silicon carbide separates into SiC, Si and then C react with the Al and then form Al4C3, and 3 silicon is left, and the 3 silicon goes into the matrix material nearby and modifies the chemical composition of the aluminum alloy also. Therefore, this separation takes place only at the surface, on the surface of silicon carbide. So L4C3 degrade the mechanical property as well as physical properties. And not only that, if you try to control this formation during your processing, sometimes in the working environment, if you have a humid condition or some kind of acidity condition, it tries to form, or kind of an elevated temperature condition, it tries to form Al4C3. So you cannot stop, you cannot avoid this. Somehow or other, one way or other, this byproduct will be formed, either during the processing condition or during the service condition. So therefore, one way to stop this degradation or Al4C3 formation is that to coat the particle. So you can coat the particle, and we have also studied this. You know what effect this will do on the mechanical property, whether it is creating good bonding or a kind of a worst bonding. And we have taken a silicon carbide plate, and then we try to create a bonding at a different temperature and studied the macroscopic layer here where no Al4C3 is formed. And with the detailed analysis with the EDS and mechanical property, putting this subjecting to a what is called the tensile condition. So we studied the mechanical strength and the bonding, also very, very poor bonding. It can be easily separated with a minimum load. So, and also the separation, L4C3 formation is more and more with respect to temperature. When the working temperature, melt temperature is higher, you form more amount of L4C3. As a result, it is weakening the composite system. And this formation is also experimentally demonstrated and confirmed with the XRD analysis, where you form L4C3 at the junction, at the macroscopic junction. We have also computed the diffusion length. So what length this will penetrate, this L4C3, and it would form up to 0.016 micron layer thickness. So that means it's a very fine precipitate, but the effect would be very, very adverse effect. So here it says that with increasing the working temperature, melt temperature, the amount or length of the diffusion is also high. That means you can able to form some good thickness layers of precipitate which covers the particle. Okay, over that, as a result, the bonding is stopped, permanent bonding is stopped. So these are some macroscopic images of that, where how it establishes the bonding. And also we have done some EDS analysis to understand how the free silicon modifies the what is known as the composition of the material. So that also we have studied. And finally, so we can also study the interface formation with the micro hardness examinations. And from the interface to away from the interface, we can establish some correlation where L4C3 formation try to create more hardness at the interface. Away from that, it is decreasing. That means it's a hardness of the original material. So this ex-situ reactions, because the problem of the homogeneous distribution and interface bonding mechanism, that can be eliminated by developing the same reinforcements by in situ reactions. So especially in the in situ reactions, you have a gas liquid reaction, liquid solid reaction, and these two reactions are there. And especially one reaction that we have demonstrated is liquid solid reaction. That means, we take a precursor solid of K2TiF6 and KBF4, and aluminum is the matrix material. And these reactions will produce TiB2 ceramic particle into it. So this is a procedure. I will skip it and I will demonstrate what is the real thing behind this in situ reactions with microstructure examinations. See, after developing these reactions inside the melt, one could see that at any temperature, whether it is 700 degrees centigrade or high temperature, I could be able to get the distribution of reinforcement homogeneous, because the particles are evolved in the what is called inside the liquid melt. So there is a homogeneity in getting the particle, and also the particle has uniform dimension homogeneously. And also these are all the particles which are separated and take an examination where you have some particle which are some spherical shaped and different shape formations are there. And so with this, we could be able to say that which gives a homogeneous distribution that can be demonstrated by measuring the hardness along the length direction, across the direction. And because the distribution is homogeneous, the hardness value measured on the surface anywhere shows the homogeneous hardness value. And also there is a greater improvement in the mechanical property. And one more important interesting thing is that we could not notice any interface formation because the reaction itself gives the particle and further reaction may not be there. So the particle directly create contact with the matrix, and as a result, it create good bonding also. So the greater improvement from the original strength of 115 megapascal to 202 megapascal, which was the greater achievement, greater improvement in the strength that is possible. And also one can imagine that it can be also extended to a mass production, but there are some challenges, as I said. See, the caster, that is very, very important. The strip casting process, and also if you try to couple these fuse casting, you have to have an instrumentation to connect these two, and also a design is necessary to overcome these challenges of the particle distribution, and also try to make an in situ reaction that the in situ reaction will eliminate what is known as the interfacial formation. So the science of primary processing of EMC need to be understood more thoroughly, especially a factor affecting the microstructural integrity, including the agglomerations in MMC. So that is one of the challenges. But if these challenges are broken, then we have a good opportunity that there are possibility that we can make several component out of this MMC, especially the brake parts, brake liners, and also the aluminum matrix composite cylinder liner. Then we have a drive shaft that can be also made by aluminum carbon-based composites. Not only the cylinder running surfaces, the as I said, brake liners and piston. So many good applications that you have with this wonderful material. But so far, this real potential of this metal matrix composite been not fully exploited. So in some of the cases, people are using this metal matrix composites with some specific processing. But for a commercial production, it still has some barrier that has to be overcome. So I think with this brief my research background, I just conclude, and then probably I can take up 2-3 questions from the participants. So thank you very much.